Don't forget to subscribe and ring that bell.
Hi there, hey there, ho there. We are going to continue the 2013 AP Calculus AB examination, practice examination that College Board gave us. We are going to finish the final 8 problems from Section 1, Part B. That's problem number 85 through problem number 92. And hey, guess what? A graphing calculator is required for some of these questions. Sweetness. And speaking of graphing calculators, I personally use a TI-84 CE, the color edition, the TI-84 Plus. Mine is that cute mint green. I love it. But they have a whole slew of colors. I dropped some links in the description. So if you're on the market for one of them, check them out. They're pretty cool. I bought my son the blue one. He likes that. All right, enough of this. Let's do some calculus. Number 85. A particle moves along the x-axis so that at time t is greater than or equal to 0, its position is given by x of t equals a cosine of the square root of t. What is the velocity of the particle at the first instance the particle is at the origin? This is where you need to, take a breath and understand what they're asking you. What is the velocity? So first of all, I need to figure out velocity. Velocity is basically the derivative of position, right? I should do v of t. Okay, that's velocity. Okay, so what is the velocity? I need to know the time to plug into velocity. They're asking me, what's the velocity? So I need to know a time to put in here. What time do I put in? The same time that the particle, the first instance that particle is at the origin. Now, you might be thinking 0 and saying, well, I put a 0 in for time. No, they don't want to know at time 0, at position 0. When the particle is at the origin, that means the position would be 0. Okay, so let's look at our position formula or equation right here. And right now we have x of t equals cosine of the square root of t. All right, the position is 0. All right, what time does this happen? Whatever time that is, that's the time we're going to throw in right here for velocity, okay? So I like to think of my graph. And if you want to do the unit circle, God bless you, you can. The cosine graph, here's 90, here's 180, 270, all the way to 360. Here's 1, here's 0, and here's -1. Cosine is the cup. Starts up high, comes down here, comes down to -1, back up, back up. So cosine is this cup. So the first time it hits 0 is right here at 90 degrees. We'll call that pi over 2 in radians. Okay? That's the first time. It hits here again. That's the second instance. They want the first instance. So cosine of pi over 2 would give me 0. Okay? So the cosine of pi over 2, the cosine of 90, that's what gives me my 0. The thing is, I need to make, in order for this equation to be true, whatever's in the parentheses here has to be pi over 2. So what I'm going to do is I'm going to say, well, the square root of t has to equal pi over 2. In order for this to be true, to equal 0, what's in here has to equal pi over 2. So how do I get t alone? Well, I'm just going to square both sides. The square and square root cancel. And I square this side. So time is going to equal pi squared over 2 squared, which is 4. Because remember, I got to square the top and I got to square the bottom. So at this time, okay, my cosine of the square root of time would be 0. That's the time that I'm going to put into velocity. So I want the velocity at pi squared over 4. Okay, I don't have velocity. I have position. I could take the derivative of position algebraically on paper and pencil, but we have a calculator. So I'm just going to take the derivative of position, which is velocity, at a value of pi squared over 4, and I'm going to do it in the calculator. All right, you attached LCD. I love when we get to use the calculator right off the bat. So in order to get the calculator to give us a number from a derivative, the calculator will not give us an expression as a derivative. It will only evaluate a derivative at a certain value. It will only output a number, not an equation. Math 8. My derivative with respect to x, because we're using x, of what is position? What is the equation I'm taking the derivative of? It's the cosine of the square root of x, because we're using x instead of t, at what value of x? I don't know. Why don't we do this? Pi squared divided by 4. Negative 0.318. Okay, negative 0.318. That 8 will stay an 8 because the number after it is smaller than 5. So that is approximately negative 0.318, which is choice C. Number 86. Oh my God, I normally love graphs and tables and charts, but it looks like they gave us 5 tables, or charts, if you will. Right? 86 reads, if the first derivative of f is greater than 0 for all of x, and the second derivative of x is less than 0 for all of x, which of the following could be the table for f? All right, well, let's figure out what each one of these things represents. In terms of my original function f, which is what one of these tables could be, the first derivative means slope. If my slope is greater than 0 or positive, I should have an increasing slope or function. Okay, it should be going up. If my second derivative is negative or less than 0, that's happy or sad face. That means it's going to be a sad face. So I should have a sad face, but it should be slanting up, not down. Okay, so it should be increasing. So I should have a function that kind of looks like that. Let's take a look at all these possible tables for f. Okay, let's put this off to the side here. All right, so if I were to just quickly plot these points, negative 1, 0, 1, 1, 2, 3, 4. All right, I have negative 1, 4, which is up here. I have 0, 3, and I have 1, 1. Okay, that curves down. It's kind of curving down like that. That's decreasing. That's not increasing. I want it to have a positive slope, not a negative slope. Okay, let's take a look at the next one. Get out of here, curvy. Negative 1. Yep, that's a negative 1, not negative 0, kids. 1. Here's 4. So it's 4 here. It's 4 here. It's 4 here. That's a horizontal line. Now, you keep your horizontal line. C. Negative 1, 0, 1. It's going to be 1, 2, 3, 4, 5, 6. Okay, so negative 1 is 4. 0 is 5. And 1, which I don't have here, is 6. That's a straight line. That goes up by the same amount. So even though it increases, there's no curvature to it. It can't be that. Okay, so it's either D or E. All right, here we go. Here's the go time. Here's it. And you are always in my way, you little sexy vixen. So here we go. Move this over, move this over. Negative 1, 0, 1. Negative 1, 0, 1. And this goes 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Let's start plotting some points. Yeah, purple still. Negative 1 is 4. 1, 2, 3, 4. Okay. 0 is 5. Okay. And 1, which I have, is 7. So this goes up, but it curves up. That's a happy face. We want a sad face. It can't be this one. So just for poops and ha-has, -1 is 4. 1, 2, 3, 4 right here. 0 is 6, which is higher. And then 1 is 5, which comes back down. So it kind of does go up, but it's sad, okay? That's our sad. And now it's your time to shine. Where are you? There you are. Boop. There. There you go. We're pretty good. My answer, of course, is everything. E. Man, I look at 87 and think to myself, thank God I get to use a calculator here. Let f be the function with first derivative given by f prime of x, which equals 3 minus 2x minus x squared times the sine of 2x minus 3. How many relative extrema does f have on the open interval from -4 to 2? All right. Extrema, my friends, are mins and maxes. Okay, those are mins and maxes. All right. And if I want to know how many mins and maxes I have, these are mins or maxes. That means it's where my first derivative goes from either positive to negative, because it would go up to down, that would be a max, or negative to positive for the first derivative, which means negative to positive slope. That would be a minimum. So I want to see where my signs change for the first derivative. And they give me the graph of the first derivative. Okay? So I've just got to see where it crosses the x-axis, where it goes from above it to below it, or below it to above it. The first thing I'm going to do is graph the first derivative that they give me. On. Clear this out. Oh, the memories of the last problem. Let's look at y equals. And we have in parentheses 3 minus 2x minus x squared times the sine of 2x minus 3. Did they give me an interval? Yeah, from -4 to 2. I don't care about anything outside that interval on the x-axis. So my x minimum is -4, and the maximum is 2. All right, I don't know if 10 up and down is going to matter, but I want to be able to see the whole graph anyways. So let's see if we can see this whole graph. It's so pretty. There it is. Oh, we can see the whole graph. That's fantastic. Boom! There's my graph. This is the graph of the first derivative. Let's please keep that in mind. So you can see this good here. This is the y value, which is the first derivative. Okay? Now keep in mind, I'm looking for the first derivative to go from positive to negative or negative to positive. I wanted to change. So let's look at our graph. Anytime we are above the x-axis, my y's are positive. Okay? Anytime we are below the x-axis, my y's are negative. And if the y's are positive, that means the first derivative is positive. If the y's are negative, that means my first derivative is negative. So let's color coordinate, shall we? Okay, I'm going to highlight in green anytime. Oh, look at you. I'm going to start in the middle here. This is clearly positive in green. This little part is clearly positive. This is clearly below, which is negative. This is below, that's negative. This is below, that's negative. And this is negative. The million-dollar question is this right here. Does that just touch the x-axis and not cross it? Or does it cross the x-axis? Right now, I have one extrema, it switches right there. I have another extrema, it switches there. I have two more here. That's where my first derivative or slope changes. So right now I have 4 at these points right here. Do I have any more here? If it crosses, I might get 2 more. It might cross. I mean, I might have a little something where it gets positive there for a second. and I might get 2 more. Or I might not have any more if it doesn't cross. I'm going to have to zoom in right at that point. So let's get another version of our calculator. You can see where it is. Let's go to zoom. Oh, did I tell you how much I love the zoom box feature here? I'm going to move my little, I call him a spider dude. And I'm just going to go up a little bit. I don't got to go that high. Hit enter. Just go barely below it. And then just engulf that right there. I like the word engulf. Let's see if it actually crosses. Oh, it does. That is much more clear. Okay. Now, I don't think I got to explain to you that if we zoom in to this part right here, it does go from negative, and it's negative here, and it's positive up here. So I do have 2 more points. So I have 2 here, plus the 4 I have. Oh, so I have a total of 6. There are a total of 6 times that my first derivative changes from negative to positive or positive to negative. 6 times. Number 88. The graph of the twice differentiable function f is shown in the figure above. Which of the following is true? Okay, it looks like we have some inequalities comparing values. The derivative of -1, 1, and 0. Okay, here we go. I want the highlighter. -1, -1, -1, -1, -1. 1, 1, 1, 1, 1. Okay, I'm just checking it. And 0, 0, 0, 0, 0. Okay, so I need to find the derivative of -1, the derivative at 1, and the derivative at 0. Okay, so I'm going to compare the derivative at -1, the derivative at 0, and the derivative at 1, okay? And derivative, that is, oh, goodness gracious. The derivative at 1. Okay, I got to slow down sometimes. All right, so I don't have any coordinates. I don't have an equation. But what I do know, if this is f, the derivative is the slope of f. So let's take a look at the slope at -1, which is right here. Okay, the slope at 0, which is right here, and the slope at 1, which is right here. Like, even though I don't have exact numbers, I can tell you something for show. This is a horizontal tangent line, which means my slope is 0 right here. So slope at -1 is 0. The slope at 0, it's increasing. I don't know what the value is. I just know it's positive. Okay, so the slope at 0 is positive, which positive numbers are bigger than 0. So I have that evaluation. So right now, f of 0, f prime of 0, which is a positive number, is bigger than 0. So I can go by and I can start canceling out some things. My f of 0 needs to be to the right of f of -1, not 1. -1, that's to the left of here. -1 is to the left of here. -1 is to the right, so it can't be this one. -1 is to the left. -1 is to the right. It can't be this one. Okay, 0 has to be bigger. So the only question is the derivative of 1. It's a negative slope, so it's negative. So f prime of 1 is actually less than 0 because it's a negative value. Okay, negatives are smaller than 0, and 0 is smaller than positives. So this is how my answer should be. F of 1, followed by f of -1, followed by f of 0. Choice D. Number 89. Ooh, giddy up. This is a good problem. What is the volume of the solid generated when the region bounded by the graph of x equals the square root of y minus 2 and the lines x equals 0 and y equals 5 is revolved around the y-axis, not the x-axis? Oh, that's important. That means when I integrate because I need to integrate, okay, to get volume. When I integrate, my bounds are going to be y's. They're not going to be x's, which means my equation should have y's in them. Everything should be y's. All right? So let's graph this first to get a visual. That would be nice, kids. Oh. If I graph that, I got to solve for y. So that's going to be x squared plus 2? Yep, okay. Let me tell you, if I want to solve for y, I got x equals y minus 2. Okay? I'm going to square both sides to get rid of this. So I got x squared equals y minus 2. All right? Now I'm going to add 2 to both sides. So x squared plus 2 is going to equal y. So when I graph this, that's going to be the same thing as graphing this. All right? Now, I want it between x is 0 and y equals 5. All right? So let's go ahead and graph this thing. And that is going to be x squared plus 2, remember. There you go, y equals. Clear that out. X squared plus 2. All right, do that in red. And let's go to my zoom and go back to standard, which brings us to our standard 10 by 10 window because I was zoomed in from the previous problem. And there we go. Now, keep in mind, we want this between x equals 0 is this line right here. X equals 0. And y equals 5. 1, 2, 3, 4, 5 right here. So this line. So I really only care between my function and those two lines. I really only want this right here. So let's change some of the window. I don't want to go anything. Yeah, I knew that was going to happen. I don't want to go any more this way. So I don't care about this side of the x-axis. And I really don't care above the line y equals 5. So let's change our window so that we don't include the negatives on the x, and we don't include anything much bigger than 5 on the y. I mean, if you want to use zoom box, you can. Window. Let's start at negative 0.5. We'll go a little bit past 0. We'll go to, I don't know, let's go to 7. And on the y's, I don't want anything negatives. I go to negative 0.5 to 0. And I'll go to, I don't know, 5.5. Okay, because I only want to go a little bit above 5. So now I see this right here. Bam. Let's bring this out. There you go. This is the graph of this. Okay, so between this x equals 0 and this y equals 5. Okay, here's my section. This is my R. Okay, this is going to be revolved around the y-axis. Okay, revolved around the y-axis. Okay, so whenever I revolve anything, up there, kind of smaller here, it's going to create the shape that looks like this kind of big bowl. All right, where's it going to be? It's going to be from a y 5 and the lower bound right here. This is 1, this is 2, and y is 2. So those are my bounds. So I'm going to integrate. Okay, anytime I want volume, I integrate the area of my shape. Notice that these are circles. Okay, so I'm going to integrate the area of a circle. Let's go. Let's do this. I'm integrating. This is pi r squared, okay? And the pi is a constant, so that's going to go on the outside. Pi r squared. My bounds are from 2 to 5, 2 to 5, and my radius is my function, square root of y minus 2. Okay, that's my radius, because my radius, let me do this in a nice orange, goes from here to here. I don't know if you guys can see that too well. Okay, that right there is my radius. And that's just the value of my function right there. That's it. So It's my radius square root of y minus 2 squared dy. This is what I'm integrating. Okay, the setup, the explanation for that setup was much more difficult than actually doing this because we got a calculator. Now, in the calculator, we're not going to put y. We're still going to put an x for here and here. Okay? Just like if y was a t, in the calculator, we still put the x in. Here we go. So I've got, let's get out of here, math 9. From 2 to 5, it is in parentheses, the square root of x minus 2, parentheses, that's the radius. But remember, we need the radius squared. dx, bang, and we should get 4.5. All that work. Oh, what did we not do? We forgot. What's our little friend that's in front of our integral here? It's pi. A pi should be in front of that integral. So, I mean, I could multiply this times pi, but let's just do it nice and clean. Pi. Now it's in front. There you go. 14.137. Choice E. Number 90 is a lot like a short answer problem. So this is going to be, buckle in. Get ready to do some algebra. The population P of a city grows according to the differential equation dP over dt equals Kp, where K is a constant and T is measured in years. Okay, this is important. So I'm going to just, K is a constant, all right? I like that soft purple. If the population of the city doubles every 12 years, what's the value of K? All right, well, the first thing I'm going to do is I realize I need to come up with an equation. I'm going to have to do separable differential equation right here, which means if I have dP over dt equals Kp, I want to get my P dP on one side and my K dt on the other. So I'll multiply this by 1 over P. This goes bye-bye. I multiply this by 1 over P. Okay? The left side, I'm going to multiply by dt. So this goes bye-bye. And I multiply this side by dt. All right, so what does that leave me with? 1 over P dP equals K dt. And that's fine. Remember, you don't need a t with a dt because K is a constant. Think of it, maybe it's 4. Maybe it's 3. That's fine because now we are going to integrate both sides. Oh, you should know your rules for integrals. Ooh. This is going to be the ln of P. Don't forget, there are no bounds, so I need to do plus a constant equals. If I have a constant here that's 5, and I integrate it, it becomes 5t, or 5x. But I have a k, so I'm going to make it kt plus c. Again, this is a constant, that k. It's a number. That's not a variable. All right? Keep in mind that, yes, I have 2 constants, but they might not be the same constants. So I'm going to call this constant 1 and constant 2. All right, so the first thing I'm going to do after that is I want to get an equation where I have P equals for population. Okay, I want to get the equation that helps me find population. So let's get this constant over. Subtract C1 from both sides. So I've got my ln of P equals KT plus, if I have one constant and I subtract another constant, that will still leave me a constant. Try it sometimes. Try it for hours in a room, kids, all by yourself. Just add or subtract any 2 constants and see, you're going to end up with another constant. All right, so here's what I got. Now, I've got the ln of P, which is nice, but I want P equals for my population. So We're going to do this nasty trick that some mathematicians don't like, but you know what? It works. So, you know, poop on them. I'm going to create a base E for both of these sides. These cancel, and I have my P. God, I love this number, or this color. It's a great color. Now, what about this right here? You better know your rules for exponents. What do I mean? If I have x squared, okay, times x to the fifth, don't I just add the exponents 2 plus 5? That's really x to the seventh, right? So we're not starting with 2 and putting together to make 1. We're starting with 1. We're going to break it up so it's 2 with a common base that we're multiplying together. Okay? So basically, what we have instead of x, we have an E here. And what we have instead of 2 and 5 is we have K, T, and C. K, T is the exponent, and C. All right? So this is going to be E to the K, T times E to the C. Guess what I'm going to say to you, kids? E is a number. It's not a variable. It's 2.718, etc., etc., which means any constant raised to a constant is just a constant. Sorry, I don't mean to throw that off. Now, let's just put our constant out front here. So P is going to equal some constant times E to the K T. All right, so we need to figure out what C is. That's the first problem here, okay? And how am I going to do that? Because they don't really give me an initial condition. So let's go all the way back up to our problem. Told you this is like a free response question. The population doubles every 12 years. Well, T is time, right? So let's come up with a little scenario down here. We got P equals C to the EKT. Let's get rid of this. We'll go back here, and let's continue. We have C equals E. Yeah, I'll be okay. P equals CE to the KT. Well, at time 0, at the beginning of our thing, let's call our population, we can call it anything. Let's make it simple. 1. Well, every 12 years, so at time 12, our population doubles. So our population would be 2. That's it. I could have made this 5,000 here. Then this would have to be 10,000 here. It don't matter as long as it doubles in 12 years. But I'm going to stick with 1 and 2 because those are easier numbers to use. All right? Now, I'm going to use one of those coordinates to solve for C. Yeah, that's another reason I like to use 0 and 1. Okay? When time is 0, my population is 1. So let's go ahead and do that. Let's go back to that cool color. Oh, there it is. 1 equals C, which I'm trying to figure out, E to the K times 0. Oh, it doesn't matter what K is right now because anything times 0 is 0. And anything to the exponent of 0 is 1. So guess what? 1 equals C. This is going to go right here in my equation. So now, let's rewrite my equation. P equals 1C. I mean, I don't have to write the 1. I could say 1e to the kt. All right? But really, when I have the number 1 times anything, it's like you don't have to write it. Okay, there you go. So now, here's where our second coordinate comes in handy. I still need to find k. That's what they're asking me. What value of k? Well, when time is 12, guess what population should be 2? So the population is going to double to 2 when my time is 12. So basically, got 2 equals e to the 12k. I could do this algebraically, then plug it in a calculator, or I can graph them both and see where they intersect. I've already done so much algebra, I'm just going to continue doing algebra. But if you wanted, you can put this one into y1 and this side into y2 and check where they intersect. But I'm not going to do that. No. I, my friends, am an avid fan of mathematics. So I'm going to take the natural log of both sides. Okay, so the natural log of 2 is going to equal, these cancel, 12k. Now I'm going to divide both sides by 12. Okay, so my k is going to equal whatever this is. So I'm going to put that in the calculator instead of graphing them both. I don't know. I just like to do that. If you couldn't have done that last part, again, graph 2 and y1 and graph e to the 12x in y2. But I have the ln of 2 divided by 12. When everything's all said and done, I get 0.577. This will go up to an 8 because a number after it is 5 or bigger. Okay, 0.058. So K is approximately 0.058. Let's look at our answers. Man, I told you this was like a free response question. 0.058, that's choice A. There you go. All right, after that nice long problem, I think we got two shorter-ish types of problems coming up to end. And number 91, the function f is continuous, and the integral from 0 to 8 of fu du is 6. What is the value of the integral from 1 to 3 of x, f of x squared minus 1 dx? What you need to realize here is we got to kind of compare these two because we're going to have to use this 6. All right, highlighter. We got to compare these two, okay, this to this. Okay, how so? Because we're probably going to have to, the 6 is going to come into play. All right, that 6 is going to come into play big time. All right. Oh, that blue is still exposed. Probably can't see it on your small phone, but it's bothering me in my OCD. So here we go. If I were to solve this one on the right side to make it look like the one on the left, all right, if I want this integral to kind of become this, then I can set it equal to 6 and it would really help me. I'm going to use u substitution. I'm going to say u is x squared minus 1. So du is 2x dx. However, I only have an x and a dx. X dx. I've got to get rid of this 2 on the right side. So I'm going to multiply by a half and multiply this side by a half. So 1/2 du is going to go in for x dx. Now, you may be saying to yourself, how would you know to even make this u, this x squared minus 1? Simple. Let's go back to our fancy color in the thicker one. You see this right here? I want to make this so it's f u as well. That means what's inside has to be u, doesn't it? It does. Okay, so let's, f u. That's great. Anyways, okay, I have my new integral. In for this expression is my u. So that's where my fu, that's where my fu is coming from, okay? Now, I'm going to take x dx out, and in its place, I'm going to put 1/2 du. My constant of 1/2, I'm going to put on the outside, du. All right, so now it looks very similar. What about my bounds? My bounds were from 3 to 1. When x was 3, okay, that means I got to throw a 3 in here. 3 squared minus 1 is 9 minus 1, which is 8. Well, you look at that. It's the same thing as this upper bound. Loving it. What happens when I throw a 1 in? Okay, when x is 1, I got to throw that in here. That's 1 squared minus 1, which is 0. Beautiful. That's one right there. So the equation or integral on the right has now become the integral that I have on the left here, which should equal 6, except, notice there's 1/2. Notice this 1/2 isn't here. So really, without the 1/2, okay, this integral right here is 6. Okay, that integral right there is 6. All right, so ready? I'm just going to substitute a 6 in for my integral. What's 1/2 of 6? 3. Bing, bang, bong. Those 3 words all begin with a letter B. You know, yeah, I'm cool like that. So that's it. We just found the value of that big, long mess using that F of U they gave us. Hey, F U. It's important, kids. Finally, number 92. The function f is defined for all x in the closed interval from a to b. If f does not attain a maximum value on a to b, which of the following must be true? Okay, must, not could be true. Must be true. All right? Here you go. Must be true. It does not attain the max value. This is all explanation and understanding. It's really no calculus. So I'm just going to draw some things really quick here. F is not continuous. That is obviously, okay, that is obviously, to me, the answer glaring continuous. That must be true. How so? Do you see the fact that f does not attain a maximum value? It doesn't mean it doesn't increase. That means at some point, the derivative can't be found if it's not continuous. Okay? The derivative cannot be found. Okay? If there's points everywhere, okay, if it's defined everywhere, okay, that means the derivative can't be found, okay? Which means it's not continuous. It can be continuous and not have a derivative. But if it doesn't have a derivative, it cannot be continuous. F is not continuous. That's the best thing. So I'm going to have something go up like this, and then, oh, guess what? Oh, there's where the max point is, there's a hole. You can't find the max there, can you? You can't. And that's what A is. F is not bounded. I mean, on A to B. Maybe it is. Maybe it's bounded above and below. I mean, that could be true. It doesn't have to be true. F does not attain a minimum. Oh, yeah, it could. It's just saying nothing about a maximum. This could be true. It doesn't have to be true, though, see? The graph of f has a vertical asymptote in the interval. Maybe it does. Maybe it doesn't. I don't know. I mean, it doesn't have to be true. And the equation f prime of x equals 0 does not have a solution in the interval from A to B. Okay, that could be true, but it doesn't have to be true. Like I can, you know, I can have a corner or a cusp here, and I can say, well, my first derivative, I mean, that's undefined there, but it's continuous, okay? It doesn't have to equal 0. That can have a max point and not equal 0. It could be undefined. So it can't be this one. It has to be A. That sure was one wild and crazy ride. Multiple choice toward the end always get nuts. So we are going to continue this journey on the next video I post. That will be when we start the free response questions. I mean, I think there's 6 of them. We get a calculator for 2, and 2 of them or 4 of them we don't get a calculator for. Weird. Anyways, hopefully I'll see you then. Bye-bye.
Don't forget to subscribe and ring that bell.